Hey gang, welcome back to 4600. Today we're going to move into section 5.4, which basically goes over the idea of independence with multivariate probability distributions, both discrete and the continuous variety. And there's really no justification in the book for why this is important, but it's nonetheless important to know when things are dependent versus independent, because it happens to do something. It's going to have the reason why we're looking at it now is because when we talk about something called covariance in a couple of sections from now, the idea of covariance also has something to do with when bivariate distributions are either independent or dependent. And when I say independent or dependent, that means that the random variable y sub 1 is independent of y sub 2, and when those happen, we'll see later on that the covariance values will equal a certain value, and otherwise they won't. And so this is kind of a precursor to that, which comes a little later, but we're going to go ahead and just talk about how you show that a multivariate distribution is either independent or dependent. Okay, as this harkens back to chapter 2. When we were talking about basic probability. I say, so if two events were independent back then, we had this little formula here that we could use to prove that two events were independent, and that was if the intersection of the two events, A and B, the probability of that, was equivalent to taking the separate events, the probabilities of the separate events, probability of A, and then multiplying by the probability of B. If that equation held true, then we were talking about independent events. Otherwise, they were called dependent, one dependent on the other. And recall what independent events means. It means that the probability of one event doesn't affect the outcome of the other. In other words, they're independent of each other. And when they're dependent, that means that they do. And so we've seen probability problems like that in the past, where, like for example, flipping a coin multiple times is considered an independent event. Versus like maybe drawing a card one at a time from a deck is a dependent event, because the probability changes from each time you draw a new card. And so that's just kind of a reminder what independence and dependence is, probabilistically, that is. When discussing random variables, though, if we have some value A, which is less than B, and another value C, which is less than another value D, we're often concerned with the events of the type where y sub 1 falls between A and B, or basically in between A and B, and where y sub 2 is some value between C and D. For consistency with the earlier definition of independent events, if the random variables y sub 1 and y sub 2 are independent, we would ultimately like to have a similar formula like this here, where the probability of A being between, or probability of y sub 1 being between A and B, and C being between, and y sub 2 being between C and D, is equivalent to the separate probabilities multiplied together. So the same concept still applies here. And this is true for any choice of real numbers such that A is less than B and C is less than D. And so that is, y sub 1 and y sub 2 are independent. That is, if y sub 1 and y sub 2 are independent, the joint probability can be written as a product of the marginal probabilities. So these two guys would be technically, in the case of what we've been looking at from the last section, these two would represent the marginal probabilities along with the joint probability. Okay, so we've got that going on. So a couple of definitions here on the first few slides from the textbook. This first one just basically says if you have a distribution function, capital F sub 1 of y sub 1 for the random variable y sub 1, and similarly for y sub 2, you have a distribution function, capital F sub 2 y sub 2, and in y sub 1 and y sub 2 you have the joint distribution function, f of y sub 1 and y sub 2. Then those two independent random variables, or those two not independent, but those two random variables are said to be independent if and only if, very similar to the formula we've been seeing, the joint distribution function is equal to the two marginal distribution functions. So these are kind of like representative of the marginal or the distribution functions for for y sub 1 and y sub 2 separately. Okay. And this has to be true for every pair of real numbers, the ordered pair y sub 1, y sub 2. So if those two random variables are not independent, we'll call them dependent, right? That's kind of the way the independence has always worked. All right. So the next slide's got the theorem 5.4 on it, which is kind of really where we're going to live formulaically. And the first case here is the discrete case. All right. So if we have our two discrete random variables, right, if they're discrete, and we have a joint probability function of the probability of y sub 1 and y sub 2, and the marginal probability functions p sub 1 of y sub 1 and p sub 2 of y sub 2 respectively, then if this formula holds true for all pairs of real numbers, for all ordered pairs, then we'll say that that the distribution is that y sub 1 is independent and y sub 2 are independent. Okay. And that has to be in this case, the all pairs thing is very important, because with discrete values we can actually look at all the different ordered pairs in most of our scenarios we've seen. So it has to be true of all of them. If you find that it's not true for just one scenario, one ordered pair, if one ordered pair y sub 1 and y sub 2 doesn't make that equation equal, then we'll say the whole thing that they're both dependent on each other. So y sub 1 and y sub 2 would be dependent in that case. We'll see a couple of examples of this here in a moment. And in the continuous case is below, and it's a very similar definition, except for they just replace the discrete notation with a continuous notation here. But if y sub 1 and y sub 2 are continuous random variables with a joint density function little f of y sub 1 and y sub 2, and the marginal density functions f sub 1, y sub 1, f sub 2, y sub 2 of y sub 2 respectively, then the two random variables are independent if and only if they satisfy this formula. Now in this case, we don't have to check it. We don't always have to check every outcome, because we're talking about integration here, right? And it would be impossible to do that with a continuous function. So really this comes down to, are the functions is the joint density function, this guy, equivalent to us multiplying the two marginal density functions together, right? And again, that's for all pairs of y sub 1 and y sub 2, but in the continuous case, we won't be able to check them all. So we're really more interested in the function here. With the discrete case, we're more interested in the actual probabilities. Okay. So this first example shows a discrete case, and we're trying to show that y sub 1 and y sub 2 are independent. For the die tossing experiment that was mentioned in section 5.2, this is the one where we had two six-sided die and we rolled them both, and y sub 1 represented the number that came up on die 1, and y sub 2 represented the number that came up on the second die. All right. So recall from that experiment that the probability of y sub 1, let me write that a little bit better there, y sub 1 and y sub 2 for any ordered pair was 36, 1 over 36, right? And that's for all combinations y1, y2, and y2, right? That was true in any case. Because remember, the very first time I did this example, I drew the little contingency table with the 1 through 6 representing y sub 1 across the top, 1 through 6 down the on the side representing the y sub 2 variable, and we said it was to roll a 1 and a 1 was a 1 in 36 chance. The same thing would be true of rolling a 1 and a 2, 1 and a 3, so forth and so on. So they were all equivalent probabilities. what we also did when we talked about marginal probabilities, the following. So we also discussed that the marginal densities or marginal density, I should just say marginal density here, for the random variables y sub 1 and y sub 2 were p sub 1 of y sub 1 was equal to 1 out of 6 for y sub 1, for any y sub 1 value that we chose, and p sub 2 of y sub 2 was also equal to 1 over 6 for any y sub 2 value we chose, right? And recall that y sub 1, since it was a 6-sided die, those values could fall between 1 and 6. And same thing for the y sub 2 variable. Those numbers on the second die could take on any number between 1 up to 6. But that was true of any case. And recall that the marginal density p sub 1 of y sub 1 was equal to, for example, let's say y sub 1 was just 1. Then that was the probability that we rolled a 1 and a 1 plus the probability that we rolled a 1. We're keeping the y1 variable consistent here. It was 1, 2 plus probability we rolled a 1, 3 all the way ... plus probability that we rolled 1 and then a 6. And so there were 6 outcomes total if we listed them all, and that ended up being 6 over 36 or just 1 over 6. That's where those numbers are coming from. All right, I'm not going to keep that up there though. So let's just take an example here. So say we let y sub 1 equal 1 and y sub 2 equal 2. So rolling a 1 on the first die, a 2 on the second. That implies that p of y, if we take the definition of the theorem, the previous theorem on the slide before, p of y sub 1 y sub 2 for this to be independent has to equal to p sub 1 of y sub 1 times p sub 2 of y sub 2, right? And so that was like saying p of 1 comma 2, the probability of that has to be equal to p1 of 1 times p sub 2 of 2, the value 2. And this equals 1 out of 36. And each one of these equals 1 over 6, which does equal 1 over 36. So that's one scenario. I don't need you to show me every scenario if you explain the stuff up top here for a problem like this. But when I said it has to be true across all of them, you've got to give me a good clean case that you're showing or telling me some way that you know that all the probabilities are going to come out to be similar to this, so that you don't have to show them all to me at one time. So we can really wrap this up and say, thus, it can be shown that p of y sub 1 and y sub 2 is equal to p sub 1 of y sub 1 times p sub 2 of y sub 2 for all y sub 1, y sub 2. Therefore, the random variables y sub 1 and y sub 2 are independent. And I will just state this, this being a 4,000 level class, when you do write stuff out, you can't just give me the answer they're independent. You got to show me that you know that's the case. It's kind of like mathematically you have to prove your case, and so make sure you do that for me, because if you don't, then I'm just going to assume like, well, okay, you got the right answer, but how did you know that? Make sure you justify your case here, and everything I've written here is not what I expect everyone to do, but you need to make a good case. All right, show me you know why they're independent or why they're dependent. When something's dependent, it's a little quicker, because all you have to do in the dependent case is find a case where this equation right here doesn't work out. If you find one instance of that, then you can say that y sub 1 and y sub 2 are dependent, all right? But in the case of like this problem, you have to kind of like lead me into knowing that that all cases work out the same way, all right? Whether you show me them all, which is fine. If you want to do that, that's a lot more work than you need to do, but just make a good case for me, okay? Example 2 is from the textbook as well. It's example 5.10 from the textbook, and it's going back to an example we've done in another lecture and previously in the book about the Republicans. It was like there was like a certain number of Republicans, a certain number of Democrats, and like one independent, and they were choosing a committee of 2 people, or I think it was either 2 or 3. And so y sub 1 represented the number of Republicans, and y sub 2 represents the number of Democrats for the random variables in this case. And they want to know is the number of Republicans in the sample independent of the number of Democrats? Well, using theorem 5.4, we just need to show that p of y sub 1 to show what, if we wanted to show for it that it were independent, we'd have to check every case here, and that's every case for p of y sub 1 comma y sub 2, that is that they're equal to p sub 1 of y sub 1 times p sub 2 of y sub 2, right? That's what we'd have to do. In this case, we're going to really quickly find out that this is not independent at all by just checking the very first scenario. And the scenario I'm going to check out is p of 0, 0. Is that equal to p sub 1 of 0 times p sub 2 of 0? And if I look at my table, p of 0, 0 is represented by the 0 right here. That's the probability of that. All right. And that's equal to the individual probabilities. So p sub 1 of 0 is going to be this 3 over 15, this column total for y sub 1 when it's 0. All right, so I'm just looking at this total in that column up down there, and that's 3 over 15 times, now I'm looking at for p sub 2 of 0, for the marginal probability of when y2 equals 0, I'm looking at this row, but I'm taking the total there, and that's 6 over 15. Those are definitely not going to multiply to give me 0, right? So therefore, we can say that 0 does not equal that, and thus y sub 1 and y sub 2 are dependent. So these aren't terrible problems. This will probably be a quick lecture. But we're going to do a couple more examples just to kind of see some of the continuous cases and and one other theorem here in a minute. So example 3 is the next example in the text, but it's a good example. And they want us to show them that y sub 1 and y sub 2 in this case for this continuous bivariate function or joint function, the 2 random variables are indeed independent. Well, we have to use the formula that we saw on that slide, which says we need to take the original function f of y sub 1 and y sub 2, and we have to show that it equals the marginal functions f sub 1 of y sub 1 multiplied times f sub 2 y sub 2. Okay, and so that's what we have to show in the end, but we need these 2 marginal functions before we can show this. So that's always going to be the first step with a continuous one, is figuring that out. And so this is no different than what we've done before when in the last section when we found the marginal distribution. Y sub 1, y sub 2, and they're both between 0 and 1, but so they're all in this box right here, which will help us set up our marginal distributions. And so I first need to find f sub 1 of y sub 1, which in this case is going to be the integral of that function here, 6y sub 1 y sub 2 squared, with integrated with respect to the y sub 2 variable. Remember, with the marginal, to find the marginal distribution functions for continuous when you do the opposite variable when you integrate, then what your f function is your f sub 1 of y sub 1, you do the opposite. So it's always the opposite. All right. So we just need to figure out the limits of integration, which are pretty simple with this particular problem. If we go in the y2 direction, we're going from 0 up to 1. All right, so this is a pretty simple integral here, and I think you guys probably could figure out how to do this one on your own, but I'm going to go ahead and complete it. So we've got, if I integrate with respect to y sub 2, I'm only really integrating that value there because everything else is considered a constant. But that's going to be y sub 2 cubed over 3, and dividing that 6 by 3, I get 2, and the y sub 1 is a constant. So y sub 2 cubed, evaluate from 0 to 1, should just leave me with 2y sub 1. And that's going to be over the interval 0 less than or equal to y sub 1 less than or equal to 1. So there's one marginal for the marginal function for y sub 1. Now marginal function for y sub 2, I know that looks like a g. Can't draw y's to save my life apparently. It's the same integration, 6y sub 1 y sub 2 squared, but this time we're doing it with respect to y sub 1. And again, looking back at my image, I'm integrating that from 0 to 1, from left to right. And that's going to end up giving me, when I integrate the y sub 1, that becomes y sub 1 squared over 2. Or this becomes yeah, hold on a minute, I'm like I made a mistake. Oh, I'm looking at the wrong problem. That would be why. I'm looking at my notes wrong. Apologize for that. Brain fart. Anyway, that's going to be y sub 1, so this should be 3 y sub 2 squared with y sub 1 squared evaluated from 0 to 1. Oops. So that just becomes 3y sub 2 squared when y sub 2 is between and equal to 0 and 1. So now that we've got those guys, we can kind of finish this thing up. And again, we're just trying to show that f of y sub 1 and y sub 2 is equal to the marginal distribution functions multiplied together. All right, y sub 2. And that's saying that taking just the actual function from above up here, you know, let me highlight that in red for us. It's saying, does that equal the two marginal functions, 2y sub 1 times 3y sub 2 squared? What that does, when we multiply it together, that gives me 6y sub 1 y sub 2 squared. They do indeed equal each other. Thus y sub 1 and y sub 2 are independent. All right. Cool. So that's pretty much what you have to show when you're doing this kind of problem here. You're either going to show they're independent or dependent one way or the other, and as long as we satisfy that equation, like I've been saying, they're independent. What about this guy? So this is another similar example. They're saying let's show that it's dependent. Okay. There's a couple of reasons why we could probably assume this would be dependent, even though they didn't tell us that in the book. And they won't always say, they'll just say, are they independent, or they'll ask if the two random variables are independent most of the time. But there's a kind of something we should look at that might lead us to believe that they could possibly be dependent from the get-go, and it's the limits they're giving us here for the distribution function. Notice that y sub 2 is dependent, and y sub 1 is dependent, and that y sub 2 has to be less than or equal to it, right? So those two variables are kind of held together within the same inequality. Therefore, they're kind of depending on one another. So that might be a giveaway that these would be dependent, but you still have to show it, all right? And so we're still going to do the similar thing that we just did where we find the marginal probabilities. Keep one. Apparently, I like to write 2's. Y sub 1, y sub 2. They're both between 0 and 1. But that y sub 2 less than or equal to y sub 1 leads me to believe that I need a line with a slope of 1 going up this way. So that's when y2 equals y sub 1. And when y2 is less than or equal to y sub 1 below that line. So that's our valid area that we need to integrate for our marginal functions. And so f sub 1 of y sub 1 is going to be the integral of 2, taking it from right there, with respect to y sub 2. And if we're going in the y sub 2 direction from bottom to top, we're going from 0 up to that line. So 0 up to y sub 1. All right, which is going to equal 2 times y sub 2 evaluated from 0 to y sub 1, which just equals 2 y sub 1. For 0 less than or equal to y sub 1 less than or equal to 1. And we got marginal distribution function for y sub 1 done. Now find the marginal distribution for y sub 2. It's going to be 2 with respect to the y sub 1 unit, or y sub 1 variable. And our limits of integration this time are going to go from left to right. So the furthest left we can go is that diagonal line there all the way out to 1. So we're going to go from y sub 2 up to 1. All right, and that gives me 2 times y sub 1 after integrating from y sub 2 up to 1, which means I get 2 times 1 minus y sub 2 as my answer from 0 less than or equal to y sub 2 less than or equal to 1. And there are my two marginals. And last but not least, to show that they're dependent, we can say, well, we're showing that f of y sub 1, y sub 2 is not equal to f sub 1 of y sub 1 times f sub 2 of y sub 2. And that's saying 2, the original joint function. And we're trying to see, is it equal or not equal to, in this case, 2y sub 1 times 2 times 1 minus y sub 2 for the second function. And we could multiply those together if we wanted to, but that we don't need to. There's no way both sides of this are going to equal each other anyway, because on the left hand side we don't even have a variable, right? We just have the number 2. So these are not going to equal each other, and so thus y sub 1 and y sub 2 are dependent. Okay, so that's all there is to it. Just show that they're not equal and you show the dependence. All right. The next theorem kind of is kind of helpful in some ways. It's not always helpful. I prefer you showing me the ways that we just did to show me truly whether they're dependent or not. But this is another way you can do that, especially for independence. It says let the random variables y sub 1 and y sub 2 have a joint density f of y sub 1 and y sub 2 that is positive if and only if y sub 1 falls between a value a and b, and y sub 2 falls between a and d, c and d. What that's basically saying so far is that if you've got two values and two separate inequalities like this, basically that's what they're kind of pointing out without saying it directly. So you've got two separated inequalities. Then for any constants a, b, c, and d, and then you have the function equals 0 otherwise, then y sub 1 and y sub 2 are independent random variables if and only if this is true. F of y sub 1 and y sub 2 equals a function of g of y sub 1 and times a function h of y sub 2. So basically that you can separate your original function into two different functions themselves that multiply together. which means you don't have to find the marginal probabilities to do this, because these don't represent marginal probabilities. They just represent you actually pulling the original function apart in such a way that they're still a function of y1. One's a function of y sub 1 and one's a function of y sub 2, so that when you multiply them back together, they give you the original thing. So it's just kind of like a factoring trick, so to speak. And in the cases of both of these, g of y sub 1 has to be a non-negative function of y sub 1 alone, so it can only have y sub 1 involved in it. And h of y sub 2 is also non-negative, of just with nothing but a y sub 2 variable in it. So you have to really be able to separate them. Looking at the previous two examples before I do an example using this, the reason this one's dependent is because we look at the original function. We could technically say that, call that 2 times 1, but those aren't variables of y sub 1 and y sub 2, so we can't really split that apart. And the other mitigating factor here is that the inequality here, y sub 2 and y sub 1 are kind of stuck between 0 and 1 together in one inequality, whereas the definition or this theorem states that these two have to be separate. All right, they can't be in the same inequality. All right, but going back to example 3 real quick, we could have done that here because this guy is separated from this guy, and we could also probably think of a couple of different ways that we could factor this out, where we pull y sub 1 and y sub 2, the variables, apart into two different functions. As a matter of fact, that's kind of what we did when we found the marginal probabilities, right? We could have that's one possible way we could have factored those two things apart. We could have also probably done 6y sub 1 times y sub 2 squared in that scenario. All right, I still prefer you to do it the way I did this one here, but this theorem is kind of nifty, that it kind of shortchanges or gives you kind of a shortcut in certain circumstances. Don't always rely on this though, because you may not always be correct. All right, but it does help specifically when those two, when you have two separate inequalities defining your the range over where y sub 1 falls, and then separately where y sub 2 falls. All right, so an example of that is this one right here. We don't have a y sub 2 variable in the function to begin with. It's just 2y sub 1, right, for this right here. But that doesn't mean we can't split them apart. Okay. As a matter of fact, we could probably prove that this is going to be either independent or dependent regardless. And so the way that the theorem, theorem 5.5, using that theorem, we can get away with this one here. 5.5, we could have a function g of y sub 1 that only has y sub 1 involved in it, such that y sub 1 is the function we have. So it's basically like I'm splitting it apart with the 2 and the y sub 1 here. 0 is less than or equal to y sub 1, less than or equal to 1, and 0, I'm just going to put else instead of otherwise. All right, and then h of y sub 2 could just be the function containing 2 between for y sub 2 between 0 and 1, and 0 else or otherwise. Okay, so using the theorem itself, f of y sub 1 and y sub 2 is equal to g of y sub 1 times f of y sub 2, or not f, but h of y sub 2, sorry. And that's saying that 2y sub 1 is equal to y sub 1 times 2, which is true, right? That does equal 2y sub 1, and therefore y sub 1 and y sub 2 are independent. Okay. Now we could have found the marginal distributions for that one, and it probably would have given us the same conclusion. And honestly, I think that's a better way to show it than this one, because there's certain circumstances where it might not always work out that way. I know it said if and only if in the theorem, but sometimes it's hard to know exactly when you can break those things apart and get away with that and not. But the trick to it really is noticing that this is separate from this in the y sub 1 variable's limits or region or area or range is separate from the y sub 2 ones. All right, or they're defined separately. Okay, so I got one more example here, and they're wanting us to show the scenario here is dependent. The scenario here doesn't matter so much, but this is going back to something we did back in the lecture on 5.2, where we had the tank. I think it was a gas tank, and it's the proportion, and y sub 1 represented the proportion of the capacity of the tank that is stocked at the beginning of the week, and y sub 2 was the proportion of the capacity sold during the week. And so this is one of the very first ones we used to integrate or do a double integral on. But I want to show that this is dependent, that it's the y sub 1 and y sub 2 are dependent on each other, right? Which kind of makes sense because we can already see that it's going to be dependent here, but you can't give that as an excuse again. Just because you see this doesn't mean that you can always assume that, because there may be some cases where something weird happens. So I would say most of the time it's going to be true that they're dependent, but you still got to show it to me and show me you know how to show it. So I'm going to sketch out my image real quick for us. Y sub 2, y sub 1. It's not going to be to scale, but that's okay. And then we had that y sub 2 is less than or equal to y sub 1. So it's going to be that line with a slope of 1 going up here, and that's y sub 2 equals y sub 1, but we're interested only in the bottom half, where y sub 2 is less than or equal to y sub 1. So we got to find our marginal probabilities distributions for y sub 1 and y sub 2. So we're going to integrate 3y sub 1 with respect to y sub 2, and I'm going to go from 0 up to y sub 1. Alright, and that's going to equal 3y sub 1 times y sub 2 evaluated from 0 to y sub 1, which just equals 3y sub 1 squared from 0 less than or equal to y sub 1 less than or equal to 1. So we got our first marginal. The marginal for y sub 2 is the integral of 3y sub 1 with respect to the y sub 1 variable this time, since it's the marginal for y sub 2. And this time we're going from the diagonal line out to 1 of the shaded region, and that's going to go from y sub 2 up to 1. Alright, so when I integrate that, I get 3 halves y sub 1 squared evaluated from y sub 2 to 1, which is just going to equal 3 halves 1 minus y sub 2 squared. And that's over the range of 0 less than or equal to y sub 2 less than or equal to 1. So we got our marginals. It looks pretty much to me like we're going to get a dependent case here. So f of y sub 1, y sub 2, we got to show that that's equal to f sub 1 of y sub 1 times f sub 2 of y sub 2, the marginal probability functions. And the original function was 3y sub 1, and we're trying to see if it's equal or not equal to, in this case, 3y sub 1 squared was the first function, times 3 halves 1 minus y sub 2 squared altogether, which that, just clean it up a little bit. You can clean this one up a little bit if you want, but you can also leave it be, because you're obviously not going to get, when multiplying this out, it's not going to give you anything grandiose here, but that could be just simplified to 9 halves y sub 1 squared times 1 minus y sub 2 squared. There's no way that's going to multiply out, so these do not equal each other. Thus, y sub 1 and y sub 2 are dependent. I'm going to do a few more examples of these in the next lecture. Matter of fact, the recommended problems I'm giving you guys are these. And I gave you a couple of even ones, so try them, see if you can get them, and then you know, watch the next lecture to see if you got them correct. Some of them are discrete, some are continuous, so there's some good practice problems there for this to get kind of good at proving independence. All right, so that's all I'm going to say about that, and I hope you guys have a good one, and I'll see you in the next lecture video, or at least talk at you in the next lecture video. That's probably how I should say it, right? All right, y'all take care.